This morning, I'd like to talk about the first actual problem we're going to look at, which is given a function f, I want to find a solution to the equation f of x equals 0. On the graph of the function, that means the y-coordinate, which is the function value, should be 0. You should be on the x-axis. So if this is the graph of y equal f of x, we're looking for places like that, or that, or that, or that, or that. Places where the function value is equal to 0 correspond to x-intercepts on the graph. We're going to assume that the function f is at least continuous, because if we don't, it turns out the problem is basically undoable. From Calculus 1, there's a fact called the intermediate value theorem, which is going to be useful in one or two of our methods. It says if you've got a function that is continuous on the interval from a to b, and you give me any number k that's between f of a and f of b, then there is a c, an x number, c, between a and b, so that f of c is equal to k. Most people have forgotten what this is about, so I'm going to illustrate this. It's really not very complicated. I'm going to assume that I have some function f whose graph is continuous between a and b. Continuous, in loose terms, just means there are no breaks or jumps in the graph. I can draw the entire graph from x equal a to x equal b without having to pick my pen up off the paper. So if this is x equal a, there'll be some function value to go with it. If this is x equal b, there will be some function value to go with it. The function values are plotted on the y-axis. I'm looking for a number k that's between f of a and f of b. So k would be some number on the y-axis between f of a and f of b. If you draw a horizontal line so that the y-coordinates are all equal to k, if this touches the graph of f any place, then there's going to be an x number, which we'll call c, so that f of c is equal to the k number that we're talking about. And in this particular example, the horizontal line touches the graph of f here, so that x coordinate is a c number. There's another one, and there's another one. The intermediate value theorem doesn't say there can only be one. It says there's at least one. So I think if you look at this picture, what this intermediate value theorem means to us should be pretty obvious. In the method of bisection, we make the further assumption that f is not only continuous on the interval from a to b, but f of a and f of b have opposite signs. If I have that situation, and I know the intermediate value theorem, this leads us directly to what we're going to call the method of bisection. Also, later, the method of false position. So imagine you've got the graph of some continuous function on some interval from a to b, and at x equal a, the function value, the y-coordinate, is negative, and on the other end, the function value is positive. If the function is continuous, then this means there has to be at least one place, one x number between a and b, where f of x is 0, because 0 is between any negative number and any positive number. So what people could do is, we can find the middle of the interval from a to b. We can average the a and b together. This will come back and complicate things later, but we'll see that when we get there. Find the middle. Now, the function value at the middle excluding for the moment the possibility that it's actually 0, f of m is either negative or positive. If f of m is negative, as it is in this case, having a negative function value here and a positive function value here tells me that somewhere between what I'm currently calling m and what I'm currently calling b, there has to be at least one solution of f of x equals 0. So what I could do in this particular circumstance is I could forget that the left-hand part of this interval ever existed. I could start calling this number a, and now I've got an interval that's only half as big as the original interval, yet I still know that there's a solution to f of x equals 0 in there somewhere. And then we can do it again. Having thrown away the left-hand part of the original interval by setting a equal to m, I have a smaller interval. Find the middle of it and determine if the function is positive or negative. Here, it's going to be negative. So somewhere between this x value and b, there's a solution to f of x equals 0. I would throw the left-hand part away again. This new interval is 1/4 of the size of the original. Obviously, you could continue doing this as long as you feel like, at least if you're doing exact arithmetic. So we've got this situation. We've got the premise that we have a continuous function on an interval from a to b. F of a and f of b have opposite signs, and what we'll do is this. We'll go around in a loop a bunch of times. Every time we calculate the midpoint, if f of a and f of m have opposite signs, then there's a solution to f of x equals 0 between a and m. I'm going to shrink my interval by lowering the right-hand end of it down to what's currently called the midpoint. Still, assuming for the moment that we haven't actually landed on the solution, if f of a and f of b have opposite signs, this happens. If this doesn't happen, then f of a and f of m have the same sign, but f of a and f of b had opposite signs. So that's going to say that somewhere between the current midpoint and a, there's going to be a solution of the problem. So I set a equal to m. This is the end of my if then else clause. And then I go around and do it again. In exact arithmetic, you could make the width of these intervals that we're generating arbitrarily small, and you could get as accurate an answer as you wanted to out of this. As we'll see, life is not really that easy, though. We're trying to find f of x equals 0, and in the method of bisection, the intervals in which our solution is going to lie get cut in half each time. It turns out, by looking at these subdivisions, that the difference between the current midpoint and the thing that we're going to calculate, the solution to f of x equals 0, can't be any bigger than the width of the original interval divided by 2 to the k plus 1, where k is how many steps of this bisection method that we've done. It's always good to work a small example by hand using a calculator so you can understand what you're doing. So I'm going to look at the function f of x equals x squared minus 2. There are two x values for which that's 0, negative radical 2 and radical 2. I'm going to go after the positive one. Initially, my bracket AB is going to be 0 to 2. F of 0 is negative, and f of b, that would be 2 squared minus 2. 4 minus 2 is 2. f of a and f of b have opposite signs. So radical 2 is definitely somewhere between a and b. Calculate the midpoint, which in this case turns out to be 1. I have to know whether the function value there is positive or negative. F of 1 is 1 squared minus 2, which is negative 1. So f of 0 is negative 2, f of 2 is positive 2, f of 1 is negative 1. Somewhere between x equal 1 and x equal 2, the f value must be 0. So my new interval is going to be from 1 to 2. This is the first step of bisection. Then do it again. I have a new smaller interval from 1 to 2. Calculate the midpoint, which works out to be 1.5. Calculate the function value that goes with that, which works out to be 0.25. F at 1 is negative, that's this end. F of 2 is 2, that's this end. And the function value in the middle is positive. So this means that somewhere between 1 and 1.5, I have to have a solution to f of x equals 0. The bracket 1.5 to 2 doesn't tell me anything because the function values for those 2 points are both the same sign. And then obviously you can continue this process. By the time you've done the work to the end of this page, the current midpoint is 1.42185. If you'll remember, radical 2 is actually 1.4142135 some odd. So this is getting reasonably close to square root of 2, but it's slow. The progress that we're making is rather slow. Later, we're going to talk about arrays. And when we do, if we wanted to, we could store all of these A numbers and B numbers as we're going along. But logically, this algorithm is the same as what we've been talking about. There are a couple of things that we're going to have to refine later. Firstly, the method by which we calculate this midpoint. There's a potential problem with it. We will talk about that later. Also, we need some mechanism for determining whether the f of ai and f of mi have the same sign or the opposite sign. People sometimes use what they think is a clever trick, which ends up shooting themselves in the foot later. We'll talk about that later on as well. The next method that I want to talk about is Newton's method. As a prelude to this, we need to remember something. If I know that a point, x equal a, y equal b, is on the graph of a straight line, and I know the slope of the straight line, then the equation for the straight line is y minus the known y coordinate equals the slope times x minus the known x coordinate. It should be noted that this b is not necessarily the y-intercept, though. It's just a name. So here's the premise. I've got some initial estimate of the solution to f of x equals 0. Say x0, or I might call it x1, or I might call it something else. There's a point on the graph that goes with that. The coordinates of this point are the x value that I have, and the y coordinate is the function value to go with it. So if I know this initial x value, then I know the coordinates of a point on the graph. We're going to approximate the graph with its tangent line at the point that we know about. So I'm going to construct the tangent line at the point that we know about. And as a hopefully better approximation to a solution of f of x equals 0, I'm going to find not where the graph of f cuts across the x-axis, indicated by the smiley face, but where the tangent line cuts across the x-axis. This will be my new and improved estimate. If I'm happy with that, I'll stop, and if I'm not, I'll take the new x that I have, find the point on the graph to go with it, construct another tangent line, find out where it cuts across the x-axis, and repeat until I'm happy. Either I'm happy or I see that something funny is happening. So to abstract this a little bit, I'm going to assume that the current best estimate for the solution I have is x number k, and I'm wanting to generate x number k plus 1. The point xk, f of xk, is on my tangent line. The slope of the tangent line is f prime evaluated at the x that we're talking about. Therefore, because of the point-slope form of the equation for a straight line, an equation for this tangent line is y minus f at xk is f prime at xk, that's the slope of the tangent line we're talking about, times x minus xk. This is the tangent line. What we're wanting to get x number k plus 1 is I want to find the x number that goes with y being 0. So in this formula for the equation of the straight line, I'm just going to set y equal to 0 and see what happens. If y is 0, that says the negative of f of xk is f prime at xk times the x that I'm looking for minus the current x. In any numerical method, there are things that could go wrong. At the moment, since we're just looking at these introductory methods, I'm going to ignore that possibility, except maybe to make a comment off on the side. I'm trying to figure out what this x is, so I'll divide through by f prime at x number k. I sure hope I don't have a horizontal tangent line, because if I do, I've just divided by 0, and everything I say is silly from this point on. And actually, I hope that f prime of xk is not even close to 0, because if it is, this fraction could conceivably be very large, and I could go from the current location to a very far away location and not want to. We'll see more about this when we look into programming these things. For now, though, I'll pretend that there's never any difficulty. Take this formula, add x number k to both sides, and you'll find out that this x that I'm looking for, which I'm going to call x number k plus 1 in a minute, is the old x minus the function value at the old x divided by the derivative at the old x. This is Newton's method, and it's a prototypical method. It's one of the first methods that you think of. As before, I'm going to do at least a few steps of this on a problem whose solution I know. I'm going to try to solve f of x equals 0, where f of x is x squared minus 2. I'm going to try to get the positive solution, which is radical 2. My first guess, I'll call it x0. I could start at 1. That's just an indexing matter. I'm going to start at x equal 1. The next one is the previous x value minus the function value x squared minus 2 divided by the derivative 2 times x, 2 times 1, comes up to be 1.5. Then we're going to do the same thing. X number 2 is going to be x number 1 minus f evaluated at x number 1 divided by f prime evaluate it at x number 1, and having done all the arithmetic on my TI graphic calculator, I get 1.41 and then a bunch of 6s. It's probably worth mentioning the 1, the 4, and the 1 are already correct. Having done 2 steps of this business, I've already got 3 significant figures correct. So this seems pretty good. And then it gets better. X3, I typed all this stuff in on my calculator, turns out to be 1.414215686. So 1, 2, 3, 4, 5 digits correct. This is looking up. I do the next one. I took X3 and stuck it into this procedure and got 1.414213562. I saved this into the X variable in my calculator because I knew what was about to happen. I calculated X number 5, and visually, just looking at what's on the calculator screen, I get exactly the same thing I got before. But since I saved the previous one, I took my new answer and subtracted the previous one, and it turns out the difference is about 1.6 times 10 to the negative 12 power. So visually, if I didn't know any better, I would think that X4 and X5 were exactly the same thing, but in reality, they're very slightly different from each other. There's no point in continuing to compute because X number 6 and X number 7 and all of the rest of them are going to look like this. If you get your calculator out and calculate square root of 2, you get 1.414213562 rounded to the number of decimal places that we've had. So bisection is slow. At least on this example, Newton's method is really fast. As a minor variation on a theme, there's the secant method. Instead of using a tangent line, which is a straight line that the graph of the function strongly resembles close to the given point, we're going to start off with 2 estimates of the solution. The most recent one, x number k, and the next to most recent one. Instead of having a tangent line, we're going to look at the 2 points on the graph, and we're going to form what's called a secant line instead. This doesn't match the slope at the previous point, but still it shouldn't look terribly different from the function as long as the function is reasonably nice itself. The secant line is going to be through the point xk, f of xk, and xk minus 1, f of xk minus 1. I need to know the slope, which is the difference of the y numbers divided by the difference of the x numbers. The secant line is y minus the known y coordinate of this point equals the slope times x minus the x coordinate of this known point. So in this way, we actually write down a formula for the straight line that passes through the 2 points on the graph that correspond to the most recent estimate and the next to most recent estimate. Now, just as with Newton's method, I want y equal to 0 on this secant line. So take that preceding formula and set y equal to 0, and you'll get this equation. What we want is, we want this x number that makes y equal 0 on the secant line. We'll call that number x number k plus 1 after we've got done figuring out what it is. And this is not difficult. Multiply both sides by xk minus xk minus 1, and divide both sides by f of xk minus f at xk minus 1, and you'll find out that this equation must be true. And then, just as in Newton's method, add xk to both sides. So the x that I'm looking at, the newer and more improved estimate, is given by this formula. Starting off with two estimates for the solution, I will generate more estimates using this formula. This is the secant method. One way that you can think of it is it's an approximation to Newton's method, except I don't actually need to calculate any derivatives here. So I'm going to try this out on f of x equals x squared minus 2. I have to give this two initial guesses, which I'll call x1 and x2. I need to pick numbers that are reasonably close to the right answer. So I'm going to pick x1 to be 2 and x2 to be 1.5. Usually it's not all that obvious how you should pick your initial estimates. That's an issue for another time. In a moment, I'm going to make myself a table. The table is going to have my x numbers and the function values that go with them, because I'm going to need all of that information when I carry out the secant method. So x number 1 is 2, f at x number 1, that's 2 squared minus 2, which is 2. x2 is 1.5, f of x2 is 1.5 squared minus 2, which works out to be 2.25 minus 2, which is 0.25. These are going to be the first couple of pairs of numbers in my table, and as I continue calculating, I'll use previously calculated function values so I don't have to repeat myself. So x3 is x2 minus f at x2 times x2 minus x1 over f at x2 minus f at x1. And I know all of these numbers, so I'll just haul the calculator out and calculate and get 1.428571429. X number 4 is x number 3 minus the function value at x number 3 times x3 minus x2 over f at x3 minus f at x2, which works out to be 1.414634,147. The function value that goes with x number 4 squared minus 2, is 0.0011 some odd. This is already pretty small, so this thing is working pretty well. So this is the table that I had written my numbers down in. If I wanted to calculate x number 5, that would be x number 4 minus f at x number 4 times x4 minus x3 over f at x4 minus f at x3. And then you could continue doing this until you decided that enough was enough. I've checked these numbers with a little program that I wrote, and it looks like they're correct. The last thing I want to talk about today is, let's think back to bisection. You have a bracket. You have two numbers, a and b, where the function values have opposite signs. For example, the function value at a might be negative, and the function value at b might be positive. In literal bisection, you find the middle of the interval and determine whether the function value is positive or negative there. Let's say that it's negative. So you have this situation. The intermediate value theorem does not tell me that there is a solution to my problem between a and m, because a and m have function values that have the same sign. What I do know, though, is that between m and b, negative function value here, positive function value here, that there is a solution between m and b. So what we did in bisection was we just threw away the left-hand part, made the interval half as big as it used to be, and then continue. There's no strict logical reason that the point that you pick in the middle has to be the midpoint. You could pick any point in the interval from A to B, and I'm still going to keep calling it M, but it doesn't have to be the midpoint. I could look at the sign of that in terms of its function value, and then make a decision about a chunk to throw away or a chunk to keep. So in what's called the method of false position, we pick a number between A and B. We do as in bisection, but we don't necessarily look at the middle of the interval. So the premise is, as usual, I have a continuous function on the interval from A to B. The function values at the ends have opposite signs, so certainly somewhere between A and B there's a solution. Instead of picking the middle, draw the line that connects the ends, A comma f of A and B comma f B. This cuts across the x-axis somewhere between A and B. And instead of using the midpoint, use the x-coordinate of the place where the thing cuts across the x-axis instead. This has the benefit of maintaining a bracket because I'm going to throw away the part that doesn't tell me anything and keep the part that does. If by luck these secant lines kept landing right in the middle of the interval, this would be bisection. It's bisection with an enhancement. We're using secant lines to determine the M instead of just finding the middle. This chunk of pseudocode is exactly the same as our initial version of bisection, with one exception: how I'm figuring out what the M is. If you go back and you look at the formula for the secant line, if one end is A comma f of A, the other end is B comma f of B, then the place, the x-coordinate, where that secant line cuts across the x-axis is given by this formula. So I'm going to go around in a loop. I'm going to calculate this number. If f of A and f of M have opposite signs, then I'm going to set B equal to M. Otherwise, I throw away the other piece, end if, end do. If I can get bisection working, I only have to change one line in it to do the method of false position. These are our basic methods to solve f of x equals 0. In the next discussion, we're going to begin looking at various issues about how you would code these things, how you would actually write programs to carry these things out. This will be our excuse to look at Fortran functions and if-then-else clauses, and also loops, which we've already met once or twice already. Until then, I hope everyone has a good day, and I'll talk to you later.